Welcome to the Exam 1 review. So I wanted to make this just to give you a good idea of things that I think are A, important for you to know from our first section here in pre-calculus, and B, are more likely to show up on the exam. So this video isn't necessarily a promise that anything might look like this, but should be reasonably close. If you can do this and the web work, you should be in pretty good shape. And so I wanted to introduce that before we actually got started. Problem 1. Find the domain of the square root of 6 minus 11x. So here, anytime we're asked to find the domain of a square root function, we want to try two things. First, the minor one is look at the inside and make sure that we're not plugging in any problems there. So here our inside function is 6 minus 11x. And so that doesn't have any problems with its domain. There's nothing to worry about there, so we're not going to disqualify anything. After that, the most important thing when you have a square root is we need to make sure that the inside function is greater than or equal to 0. We can plug in 0 into a square root, that's fine. You can plug in positive numbers into a square root, that's fine. But you can't plug in negative numbers. So here I'm going to subtract 6 from both sides. I'm literally just going to solve this equation. So we're going to get 6 minus 11x is greater than or equal to minus 6. And now we're going to go through and divide both sides by minus 11. And we get x is now, because we're dividing by a negative number, we need to have that be greater than or equal to. And then the two minuses here cancel out, so we just get 6 over 11. And so here we were asked to find the domain. So we should give that an interval notation. Our answer should be, because this is less than, x needs to be small. We start at minus infinity. We go up to 6 over 11. That's our problem spot. And then because we can be equal to that, we put in a bracket. And so that is our answer. Problem 2. Find the domain of the fraction square root of x plus 1 divided by x minus 12. So because we have a fraction here, we need to make sure that we're not dividing by 0. That should be the first thing that sticks out. But, and this is one thing students tend to forget, we also need to check the domain of the numerator and denominator. So here if we look at square root of x plus 1, that has domain. Well, how do we find that? We set x plus 1 to be greater than 0, greater than or equal to. We move that 1 to the other side, so x has to be greater than or equal to minus 1. And now this one in interval notation would be, it has to be greater than, it goes off to infinity. So we start at minus 1. We pop all the way up to infinity. All right. And then if I'm looking at the denominator, x minus 12, on its own, so you might be noticing we don't want to plug 12 into the function. But as a function itself, this guy has domain minus infinity to infinity. But we're not allowed to plug in 0 because we need to make sure that x minus 12, the denominator, is not 0. So I check the domain of the numerator and denominator individually. And now I'm just making sure the denominator is also not 0. So what would make x minus 12 equal to 0? Well, you set that equation up, and then you simply add 12 to both sides, so plus 12 on each, and you get x is equal to 12, and so we have to get rid of that from our domain. So in other words, if we're drawing a number line, the square root is saying start at minus 1. Let's do it, give it its own color. Start at minus 1. and then move to the right. But there's a problem, and that problem's name is 12. So here, when I get to 12, what needs to happen is I need to put a little hole there and cut it out. So this is the picture of what's going on. And it's always good to have an idea of the picture, because I can get you back to what the interval should look like. Because now if I write this in interval notation, I have bracket -1, comma 12. And then I stop for a second at 12, because I can't actually plug that in. That would make my denominator 0. That's no good. And then I union that with 12 to infinity. And that gives me my interval for that function. So when you're finding the domain of a fraction, you absolutely need to make sure the denominator is not 0, but you also have to be careful that the numerator is well defined too. Number 3. Here it gives us a quadratic function, x squared minus 3x plus 6. And then part A just says evaluate f of x plus h. So we have, what is f of x plus h? And so here this is making sure that we really honestly know how to plug things into functions. Because here if I plug x plus h into this, I have x plus h squared minus 3 x plus h plus 6. So you've got to plug in the x plus h where it belongs. What some students will do is they'll accidentally put a plus h just at the end of this equation right here, this expression. But that's always going to get you the wrong answer. So don't be doing that. So we have x plus h all squared minus 3 x plus h plus 6. And so now the next thing we have to be careful of is x plus h all squared is not x squared plus h squared. That's another common mistake. So let's avoid that one. While we're here, let's distribute this minus 3. So minus 3x minus 3h plus 6. We're most of the way there. Now we just have to expand out this x plus h squared. So we FOIL that. We get x squared plus xh. And now we FOIL the h as well. We get, technically it's an h times x, but we could rewrite that as xh. We can multiply in either order. H times h is h squared minus 3x minus 3h plus 6. And so now let me grab that, push it down a little bit, because that is the answer to this part of the question. So it asked us to figure out the f of x plus h, what that's equal to. And so this was our answer here, this whole big expression. And we see, actually, we could simplify that a little bit, couldn't we? So let's do that. Plus 2xh plus h squared minus 3x minus 3h plus 6. And so we would have noticed something was weird on the next problem, even though that is a correct f of x plus h, just not as simplified as it could be. But now there was a part B to this problem that seems suspiciously easy. So now evaluate the difference quotient. So the difference quotient is given by f of x plus h minus f of x all divided by h. But then wait a minute. We already have f of x plus h. That's this whole situation in the purple box. So this is f of x plus h. We're just going to copy our answer from up here. So I'm just copying. plus 6. Now we subtract off f of x. So again, I'm really careful about parentheses here. So we have x squared minus 3x plus 6. We divide that all by h. Okay. So now on top, for that left side, those parentheses really aren't doing anything. So we just have x squared plus 2xh plus h squared minus 3x minus 3h plus 6. So nothing changed, the parentheses just weren't doing anything. But here we do need to make sure we're distributing this minus. So we get minus x squared plus 3x minus 6. We're dividing that all through by h. And now we can cancel stuff. In fact, you should be able to cancel out anything that doesn't have an h in it. If you can't on the exam, then maybe go back and check. Something probably went wrong somewhere, because these are specifically designed so that we can cancel out everything. So we have the 2x's, x squared's canceling, the minus 3x and the plus 3x canceling, and the plus 6 and the minus 6 canceling. In fact, you could do this. I'd be perfectly fine with you actually going up here and canceling them out. Because we have a minus here, any two things that look the same you could cancel. My colors don't quite match, but that's okay. Because you know that anything that matches when it's on the wrong side of a negative sign is going to cancel with anything on the left. But either way you do it, you get 2xh plus h squared minus 3h, all divided by h. And so now here the magic is everything has an h in it, so I can factor that out. So I can say this is h times 2x plus h minus 3 divided by h. And now the h's annihilate each other, they cancel. And I'm left with 2x plus h minus 3. And so that's my difference quotient. This might look really, really random, like why would we ever care about this? But it turns out if you're going on to classes past pre-calculus, this very thing comes up, and it's the backbone of what we talk about. So in calculus, it forms the backbone of the most important definition of that class. So that's the reasoning behind that. Problem 4 asks us to evaluate this piecewise defined function. So it says use 2x plus 1 if x is less than minus 3, x squared if x is between minus 3 and 5, and log base 2 of x if x is bigger than 5. And so it gives us these 4 points to plug in. So let's just go ahead. And the whole idea behind this problem is, can we read a piecewise defined function? So first we look at f of 1. And what we need to ask is, which one of these equations does 1 fall in? So we look at these 3. And we say, which of these has 1 in them? It can only ever be in one of them. Just that's how the rules of defining piecewise defined functions work. So we look and we say, okay, it's not less than negative 3, so we move on to the next one. It is between minus 3 and 5. So I can just plug in to that middle one. I get 1 squared is 1. And that's all there is to it. We just have to make sure we're using the right one. B asks us for f of minus 3. And so here's a place where it might get easy to be tripped up. Both of these equations have minus 3 in them, so I need to figure out a way to pick. And the way that I do that is I always pick the one that has the or equal to sign on it. So that says I can plug in 3 into that one. And so I do that. I get minus 3 squared. So I'm using the middle one because 3 is inclusive. And now I want to make sure I'm squaring that minus sign too to get a positive 9. All right, halfway there. C. F of 8. So again, I look at all three of these equations. Well, this looks like the one that I'm interested in, the x greater than or equal to 5 one. So I go ahead and I plug it into the bottom equation, which says log base 2 of 8. And now I hit another section in here. We have to remember how a log works. So one thing you can do is convert to exponential form. So log base 2 of x equals y if and only if x to the, 2 to the y is equal to x. In other words, what number do I need to raise 2 to in order to get 8? And so here we get that that number is equal to 3. Why? Because 2 cubed is 8. So this matches with our exponential form idea. That tells us the power that we need, which is all that log is really trying to do. All right, and then finally, f of minus 4. So this was to put in here to make sure that we were even lesson order, not just going left to right on the number line. So I look up. Negative 4 is to the left of minus 3. It's less than minus 3. So I simply plug that into 2 times x, and then it's plus 1, plus 1. So that's negative 8 plus 1 is a negative 7. And that's all really there is to it to plugging into piecewise functions. Just make sure you're in the right place with your number and you're in good shape. The one warning I want to give though is I've had experiences where students will give me 3 different solutions, and I really can't give much credit for that at all, because if you're giving me 3 different numbers, then you're making it so that f isn't even a function anymore. So make sure you're just giving me the one answer. Number 5 gives us a table and asks us to evaluate some function values. And so I wanted to go ahead and try that. First it asks us evaluate f of 7. So here if I look, I move over, I'm using my mouse here, it's a little bit easier. So I look at what 7 is, and I go to the corresponding y value. So here f of 7 is just 5. So I purely go down that table, start at the x value, go to the f of x value. Nothing too crazy. So what changes when I say f inverse instead? Find f inverse of 2. So when you're looking for f inverse, you're really saying what x value, when I plug it into f, gets me to 2. So here I want to be looking, or another way to think about it is f inverse takes in y values. So I want to figure out where is the y value of 2. We have to go all the way here to the right side of the function. And we look in the x value that gets us to 2 is 9. So f inverse of 2 is equal to 9. Problem 6 now is asking us to find an inverse function. So f of x is 7x minus 14, and it says find the inverse function to do that. So the first step is we write y is equal to 7x minus 14, and then I personally switch x and y first. So I rewrite that to say x is equal to 7y minus 14, and then I solve it for y. You might have seen this a different way where you solve for x first and then switch their roles. Either way works. They both get you the same answer. So I'm going to solve this for y then. So I add 14 to both sides. And so we get y, 7y, is equal to x plus 14. Then I simply divide both sides by 7. And I get my answer of y is equal to x plus 14 divided by the 7. And then here we can also just call this, change its name to f inverse of x. Alright. But that's the general game plan when you're asked to find f inverse of anything is swap the roles of x and y, solve for y, and then that will be your inverse function. Or you can, given a function, solve for x and then change the names later. Either way works. So the next problem takes the first one and kind of ramps it up quite a bit. So find g inverse of x if g of x is equal to this function. G of x is 2x plus 1 over x minus 3. Well, that's our fraction there. And first thing I'm going to do is I'm going to call that y instead. So y is equal to 2x plus 1 over x minus 3. Now I'm going to switch the names of x and y. So I'm going to have this be x equals 2y plus 1 divided by y minus 3. Now we're going to solve this for y. And so we have to be really careful of the algebra we're using, be a little bit technical here. But the first thing to see is I have a y in a denominator. So we're going to have to free that first. So I'm going to multiply on both sides by y minus 3. That'll save that. And I get y minus 3 times x is equal to now 2y plus 1. So we get 2y plus 1. And now on the left side, like, we need to solve for y, but there's y's here, there's y's here. At least there's no fractions anymore, but I think the first thing that would make sense to do is lay everything out so we can try to get everything that has a y in it on one side. That's our end goal. So to do that, we're going to distribute this x across. So we get yx minus 3x is 2y plus 1. And now we're still on the same mission. We want to make sure that all the y stuff is by itself. So I look and I say, what doesn't have a y then? Well, this 3x doesn't have a 1. Doesn't have a y. The plus 1 doesn't have a y. So they can go on a side together. I'm going to add 3x to both sides. And so that gets me halfway there. But this 2y is on an island on its own. This y is going to be on an island on its own. They want to be together. So we're going to minus 2y to both sides as well. And so what we're left with is yx minus the 2y that we added. The 2y's cancel. I'm left with 1 plus 3x. And so now we're really close. We can factor out a y on the left. We factor a y out of the first term, we get x. Out of the second, we get minus 2. And now the beauty happens. I divide both sides by x minus 2. Divide both sides by -2. I didn't need a parenthesis there. And we get y is equal to 1 plus 3x over x minus 2. And that's our inverse function. I'd be fine if you left it like that. But we should go back and remember that that's really called f inverse. Just to make sure there's no confusion, just to be sure we're being as clear and concise as possible. Okay, so a little bit more work, have to flex some more algebra skills, but it's not anything crazy. Number 8. When a penguin habitat opened, it originally had 25 penguins. 10 years later, it grew to 60 penguins. And so the first question is, what is the initial value for this problem? So initial value should be the thing that you start with. So we look and we say, when it opened, it had 25 penguins. So then our initial value is just that 25. It's what we started with. And so why is that important? Well, B is asking us, write an equation which represents the number n of penguins t years after it opened. And I'm going to add to that, your answer should be in the form y is equal a to the bx. So it should be in an exponential form. And the beautiful thing here is, we know the initial value. Whenever you know the initial value, it's about 5 times easier. Because we have the point 0, 25, and then it said 10 years later, we were at 60. And so now we just plug both of these points into here, and we're good to go. But because we have x equals 0, when we plug in the first one, we get 25 equals a times b to the 0. But b to the 0 is just a. So that tells us a is 25. We said in class a was the initial value for a problem like this. And so our real equation is y equals, and now we can say 25 b to the x. Now we go back and we plug in. We get 60, plugging in the 60 comma 10 now. 60 equals 25 b to the power of 10. Divide both sides by 25. So on the left side, we have 60 over 25. On the right side, we have b to the 10th. And then we can simplify the left side a little bit to be 12 over 5. B to the 10th. And now 10 is a weird power, but anytime you have something to a power and you want to get rid of it, you just take the root of both sides. So I take the 10th root of 12 over 4 is the 10th root of b to the 10. Sorry, there's a little error my tablet's been having. It's very determined to have a long one there. And so this we now just put into a calculator. So you could put this into a scientific calculator. And the way you would do that is you would say 12 divided by 5 in parentheses. You could still do this in a calculator. I'm using a web browser, but a scientific calculator would do that. And then instead of saying 10th root, it might have an option to do that. But you can also say to the power of 1 over 10. And we see we get 1.0914. So now let's just say b is equal to 1.0, and we'll round to 3 decimal places. So on the exam it would tell you how many places to round it to. So that's what we get, b equals 1.091. And so our answer at the end is 25 times 1.091 to the x. So that's the equation of our function there. But we aren't done. It also asks us to estimate the number of penguins that will be in the habitat 15 years after it opened. But all we do there is we just plug in 15 into this. So I say, okay, take all of this, raise it to the power 15. And again, we can only do that in a calculator. There's no way to do that by hand. And when I do it, I get 92.3. Here I'm going to round it to the nearest whole number. 92 because it's penguins. It doesn't really make sense to say we're going to have 92.3 penguins. So we'll just stop and say 92. That's our estimate. Alright, we got a quick one now. Rewrite log base 6 of 1296 equals 4 in exponential form. So I have log base 6, 1296 equals 4. We want to write that as an exponential. Turns out it's not anything crazy. Once again, 6 is our base. Our power is the 4 is equal to the number on the inside. So that's always how we do something like this. And the formula for that is log base b of x equals y. You can always exchange this equation for b to the y is equal to x. So that's what we're using there. You might also see a problem that asks you to do the opposite. Take something that's an exponential form, turn it into logarithm, and you just work backwards from here. Now we've got a few logarithms to evaluate. So a is log base 3 of 27. Log base 3 of 27. And so this is just asking us, what power do I need to raise 3 to? 3 to the what power gives me 27. And now I work backwards from there. And I get that x needs to be 3. 3 to the power 3 is equal to 7. Part B gives us log base 2 of 1 over 32. Log base 2 of 1 over 32. Converting this to exponential, that says 2 to what power gives me 1 over 32? So the fact that I have a fraction tells me it has to be negative. X needs to be negative because that's how I get the 1 over business there. And now I just need to know what power would give me 32. So on the side I'm going to say, what if it was just regular 32? Maybe it takes a little bit of running. You could always keep dividing it by 2 until you get back to 1. But here we get 5. 2 to the 5th is 32. So 2 to the minus 5. The minus says just flip it over the fraction. So we get x equals minus 5. And then finally we have log base 100 of 10. So this one's written a little bit sneakily. We want to say, what power do I need to raise 100 to get 10? And so we try to think, what's the relationship between 100 and 10? Well, if I take a square root of 100, that's equal to 10. But what's another way to write a square root? That's really a 1/2 power. So here we write x is equal to 1/2. And so that's how we evaluate these logarithms, is you ask, what do I need to raise the base to in order to get the number inside of the parentheses? Number 11. Expand the logarithm log base 4 of x squared y to the 9th. So what expand the log means is write it in as many pieces as possible where there's no multiplication on the inside, no powers being taken, as long as you can help it. So here we have log base 4 of x squared y to the 9th. So the first thing we do here is we use the power rule. This is equal to log base 4 of x squared plus log base 4 of y to the 9th. So there we're using the product rule. Log base b of a times b, log base b of a plus log base b of b. Now we have some powers to deal with, and we can use the power rule for that. So here the way I picture it is the powers get to go downstairs now. That's the power rule for logs, and I can say this is 2 log base 4 of x plus 9 log base 4 of y. And so we're allowed to do this by the power rule, which says log base b of x to some power p is p times log base b of x. I can always bring that power down. So that's how we expand it, is we have as many small simple pieces as we can get. Number 12. Expand this logarithm, and it's a natural log of a big, gross, stressful fraction. So we want to break that down into smaller parts. So for natural log, or any log, what we want to do is, first I'd like to get rid of that fraction. I'd feel a whole lot better if there weren't any fractions involved. So I can say this is natural log of the square root of z times x cubed minus the natural log of y to the 10th times w plus 1 squared. It's a little bit like a 9. And we can clean this up too while we're here. All right, so we've turned the fraction into 2 different logarithms. And now we can repeat what we did in number 11 and just split up these two on their own. So that first log becomes natural log of the square root of z plus the natural log of x cubed minus, and now I want to be real careful because I'm going to turn this into both 2 logs, but they should both have a minus sign because they both came from the denominator. So I should have natural log of y to the 10th, and now I split that up, plus natural log of w plus 1 squared. All right, so that's what we've got. And then what do I do from here? Well, now I see a whole bunch of powers inside of my logs. And one of these is triply a power. I have a square root on this first one. So we need to remember square root is the same thing as to a 1/2 power. And now the beauty of log is I don't have to take a square root if I don't want to. I can bring that 1/2 down instead and say this is 1/2 times the natural log of z plus 3 times the natural log of x. So now I'm using the power rule to do this. Minus 10 natural log of y minus 2 natural log of w plus 1. And so that w plus 1 might look a little bit like, is there anything we could do here? And the answer is nope, that's as simple as it gets, because logs don't have anything they can do about addition inside of them. And so even though it looked big and complex and scary, our answer just turned out to be this. Now we want to work backwards for number 13. It's asking us now to compress a logarithm. So we have 3 natural log of x plus 7 natural log of y. And so the good news is if you're good at expanding logs, compressing logs is very, very similar. It's basically just that process in reverse. So here's like a simple one. We get 3 natural log of x. That we could also call natural log of x cubed. So here the power rule is kind of working in reverse. I start with numbers in front of the log, and then because of the power rules of logs, I'm allowed to put them inside as powers. So this is the natural log of x cubed plus the natural log of y to the 7th. And that's all there is to it. So that's a quick one. 14 now asks us to compress a logarithm, but it has more pieces on it, and it has some minus signs on it. So let's see how we would work with that. So one intuition I kind of have for these things is when we see minuses, those are pieces that should wind up in the denominator. When we see pluses, here there's a secret invisible plus, right? So here, whenever something's positive, I get the intuition it should wind up in the numerator. So here what I'm going to do is I'm going to move things around so the positive stuff is together. So I'm going to have 5 log of x plus 1/2 log of z. So the positive things are friends with each other. And now minus 3 log of y minus the log of x squared plus 1. So now the negative things are friends with each other. They're next to each other. And now my next step is I've got a whole bunch of constants in front of these logs. So what I'm going to do instead is use the power rule. Say this is log of x to the 5th plus log of z to the 1/2. Okay, sorry, it's giving me a little bit of trouble. Minus log of y cubed. And now I wanted a little bit of a weird thing inside of here so I could talk about. This is an x squared plus 1. There's no log rule we can do here, though. So there's nothing that's in front of this log. And the fact that these are being added together really stops me from getting to use any of my log rules. So this just stays the same. This is minus log x squared plus 1. Now we can combine logs together. So this is log of x to the 5th times z to the 1/2 minus log of, and then it turns out these two cancel. Why do these cancel? Or not cancel, they combine. The reason why is because if I factor a negative out, this turns into another plus situation. So I factor out that minus. Now they have the same sign. They're looking at each other. They're happy. And I get log of y cubed times x squared plus 1. And now I've got subtraction going on. So I can just call this log. Gonna need to be a little bit bigger than that. X to the 5th. I'm gonna do a little bit of an exercise here, flex a muscle a little bit, make sure we're used to this. Instead of z to the 1/2, I'm gonna turn it into square root of z. And then divided by y cubed times x squared plus 1. Okay. And just to be clear, this is a z. And that is our final answer. Okay. So we just want to make sure the things that have minus signs should wind up in the numerator. More tricky, the things that have plus signs should wind up in the numerator. So that's a really, really easy thing to accidentally overlook. But this is our right answer. Now we go on to solving exponential and logarithmic equations. So the first one is 3 to the x plus 1 is equal to 9 to the 3x minus 4. So one thing we could do is we could go hardcore, take natural log of both sides, solve it that way. Or there's an easier way, one that's a lot less stressful, which is 3 and 9, they're not the same exact base, but man, they are really close to each other. We know there's a connection between them with powers. We know that 9 is 3 squared raised to the 3x minus 4. And so on the left, I still keep my 3x plus 1. On the right, I have a power raised to another power like this. So in that situation, you multiply the two powers together. So one more line, 3 to the x plus 1 is equal to 3 times 6x minus 8. And now I'm sitting here, I'm looking at this equation, and we can now use the fact that if my bases are the same on an exponential equation, then I can just say the two powers are equal. So 3 to the left power equals 3 to the right power means the left power, x plus 1, has to be equal to the right power, 6x minus 8. And so now we just solve this like a normal equation, like a linear equation. So minus 6x to both sides, minus 1 to both sides. I get minus 5x is equal to minus 8 minus 1 is minus 9. Divide both sides by minus 5. And we get x is equal to 9/5. So if we can convert, if we can make them so that they're the same base pretty easily, then we can turn this into a lot simpler of an equation. Problem 16 asks us to solve 4 to the x equals 5 to the 2x minus 7. So last time for 15, we were able to get a nice similar base, turn 9 into 3 squared. But here there really is no reasonable number that takes us from 4 to 5. So what do we do in that situation? Well, we use the fact that we can take the log of both sides. So if two numbers are equal, or two equations, then their logarithms are equal. So I get the natural log of 4x is equal to the natural log of 5 to the 2x minus 7. Now I bring powers down. X times the natural log of 4 is equal to 2x minus 7 times the natural log of 5. So that's the power rule of logs at play there that lets me do that. And now I get x times the natural log of 4. Well, I want the x's on their own side, but I've got some x stuff that's tied into some parentheses. So I'm going to distribute this natural log of 5 and get 2x natural log of 5 minus 7 natural log of 5. And now I've got x stuff on the right side. I'd rather it all be on the same side. So I'm going to subtract 2x log 5 from both sides and get x natural log of 4 minus 2x natural log of 5 is equal to minus 7 natural log 5. So we've just added that minus 2x log 5 to both sides there. And now everything on the left side has an x in it. So I can say this is equal to x times the natural log of 4 minus 2 times the natural log of 5. That's equal to minus 7 times the natural log of 5. And now, again, this looks really weird, like the natural log of 4, natural log of 5 stuff. But those are still just numbers at the end of the day. So I can divide both sides by natural log of 4 minus 2 natural log of 5. Do the same thing on this side, natural log of 4 minus 2 natural log of 5. And I get, nope, don't do that. Get x equals minus 7 natural log of 5 divided by natural log of 4 minus 2 natural log of 5. And so this is something we could put in a calculator. So one thing you might naturally ask is, well, why don't I just do something like take log base 4 so one side is easier? Well, the reason for that is if we need to put this into a calculator, there's no log base 4 button, but there is a natural log of 4 button. So I need to go calculate that to 3 decimal places. And I will be right back once I've done that. Plugging that into a calculator to 3 decimal places, we get that this is equal to roughly 6.148. And so that's our approximate answer. This on the right is called an approximate answer. It's going to have a little bit of error. This number on the left is the exact answer. It's exactly right, but it's kind of unwieldy for practical situations. So at some point we would have to approximate. So now problem 17 is asking us to solve an equation that involves logarithms. So 17 is a little bit the nicer case where we've got two logarithms like this. They have the same base. And so in this situation, if you have two logs with the same base as each other, and they're equal, then that means the insides have to be equal. So I get 1 minus 8x is equal to minus 10x minus 9. We're going to add some numbers here, so we're going to add 10x to both sides. Subtract 1 from both sides. And I get 2x. 2x is equal to minus 10. Divide both sides now by 2. Divide by 2. And we get x is equal to minus 5. And now one thing we should always do when we have a log equation is check if we have an extraneous solution. And what that means is we just want to make sure that whenever we plug them back in to our original equation, that we don't run into any domain issues. So whenever you're doing any log equation, you probably want to go back and make sure. So let's try plugging in minus 5 into the first one. 1 minus 8 times minus 5 is equal to log base 7 of 17. That's perfectly fine. 17 is a positive number. Oop. Okay, I got the wrong calculation there. Minus 8 times minus 5 is 40. So this would be 41. Okay, but still, it's a positive number, so that's fine. Log base 7 of minus 10 times minus 5, that's a positive 50. Minus 9 gives us log base 7 of positive 41. And so we're not so much checking that they're actually equal. That would be fine. But the worry would be if I got something like I tried to plug in and I got something like log base 7 of negative 13 or some negative number, because that can turn out to happen. That's called an extraneous solution. But that doesn't happen here. So our x equals minus 5 is a perfectly serviceable solution. We're happy. Last one, number 18. Solve log base 16 of x minus 2 plus log base 16 of x plus 4 is equal to 1. So this is a little bit more complicated of a log. Like this 1 here is stopping any hope that I have of turning everything into logs. And so here what I'm going to do instead is I want to have a log on one side with stuff in it, and then everything that doesn't have a log on the other side. So that way I can exponentiate everything. So here I have log base 16 of x minus 2 plus log base 16 of x plus 4. So by the combining log stuff we did, that's equal to log base 16 of x minus 2 times x plus 4 is equal to 1. Just be careful about that. And so now what I can do is I can take 16 and raise both sides to this power. So because these two equations are equal, I can say 16 to the powers are equal. That's perfectly fine to do. Plus 4 equals 16 to the 1. That's a legal move. But now what happens here, I've got 16 to the power of log of some base. Not some base, specifically of base 16. So there's one more log rule that says whenever you have a base to the log base that same thing of something, then you just get that. You get x minus 2 times x plus 4 is equal to 16 to the 1 is just 16. So now let's FOIL this out, solve it like we would a normal quadratic equation. Do all of that. We get x squared plus 4x minus 2x minus 8 is equal to 16. Let's combine the like terms that are there. X squared plus now just 2x minus 8 is equal to 16. Let's subtract a 16 from both sides. X squared plus 2x minus 24 is equal to 0. That's equation there. That's our equation now. So now I need to find two factors of 24 that multiply to be 24 and subtract to be 2. Subtract because this is a minus here, so they have to have different signs. And with a little bit of work, we get 6 and minus 4. So I plug those in. This is x plus 6 times x minus 4 equals 0. And so my first looks at an answer are x equals minus 6, x equals 4, but we have to go back and we have to check now. So let's go back to our original equation and try plugging in everything. So first I try to plug in, let's plug in 4, log base 16 of 4 minus 2, plus log base 16 of 4 plus 4 equals 1. And so you can go back, combine, but as long as you're not plugging in anything negative, it turns out it'll be okay. What we do need to be careful of, and when I say negative, I mean the thing inside of the log after you've done everything. For minus 6, we try to plug in. Again, we're plugging into this very top equation, the one that we started with. We get log base 16 of minus 6 minus 2. And we can actually stop right there without looking at the rest of the equation, because right now it says log base 16 of minus 8. Well, you can't have log of a negative number. So this negative 6 is extraneous. So our final answer is x equals 4. And you wouldn't have to write this. If you showed me the work, I would totally understand. But just so we're sure, this equals negative 6x is an extraneous solution. And so we're just left with the x equals 4.